Hi, everybody. Sorry for the last minute change. I thought that we would be able to meet together in person on Friday, but it turns out I've got another meeting, and so therefore this lecture is recorded. So this is for Friday, the 25th of March. This is class number 28. To begin with a few announcements, remember that the WMS assignment, the first one, which is having to do with some basics of watershed modeling, identifying a watershed, delineating it. So that assignment is due by noon on Monday the 28th. Please upload that to Blackboard. And then on Wednesday of next week, we're going to have an exam, which covers the material since our first midterm exam, classes 17 to 29. It's going to have a WMS problem, so you need to bring your computer for that. And it will also likely have a problem where you are using Excel. So today we're going to continue working with WMS for some watershed modeling. We'll get to national streamflow statistics using a large watershed and hurricane. So let's just dive right in. All right, so here is Google Maps showing hurricane, and the watershed that we're interested in is feeding into Hurricane Creek. And you can see that Hurricane Creek goes under Route 60 near this Road 34. And so what we want to do is we want to find out how much flow might be going under Route 60 at this crossing location. So in other words, our outlet is going to be here. So if we zoom out a little bit, it seems like the watershed, if we follow the stream, has a few different branches, but this is going to be a big one. This watershed is going to be quite large, so it may take a little bit of iteration for us to make sure that we get all of the elevation data that's going to be included in this model. But you can kind of tell from these water branches you see, here's a stream, here's a stream. So that gives you a rough idea. If you draw a line that doesn't cross any of those streams, that's kind of a basic way to delineate the watershed. So it looks like to the western side of this watershed, I've got the creek itself going under Route 60, and then to the right, how far east do I want to go? It's hard to know when you're just looking at these rural areas, but it looks like I want to get as far as far east as Scott Depot, so not quite as far as the Kanawha River. All right, so let's go into WMS and start over just in case I was working with the program earlier. Okay, so starting with the fresh model, I'm going to begin the hydrologic modeling wizard. And of course, as is always good habit, we have to save our model somewhere. So I'm just doing this in a new folder. I'm going to call this NSS example and click save and then save again. And so now I've created my file location, and then that's what tells the program where it should store all of the new things that it's going to create and download, like the elevation data file. Okay, so next, have to define a projection. So let me do that. I'll start with a global projection, and this is where I'm going to tell it that I want to be in UTM zone 17. So here, UTM NAT 83, which is the projection, and zone 17. All right. And then for the vertical datum, let's set that to this NAVD, and then the units in meters. All right. Now, define the project boundary. This is going to be a little bit tricky. It brings up the locator on my other screen because I had a couple different going. Let me type in hurricane. See if it can find that on the map. All right, it does. So you can see from this map, here's our stream, and this is where it goes under Route 60. So if I just said that this is my project location, I haven't got the whole watershed. So I need to drag it over. I think I still don't have all of it at this zoom level, so I'm going to zoom out a little bit. All right. Just glancing at it, I don't think I've got everything here either. So I have to zoom out even a bit further. Yeah, I wish it gave you like finer control over zooming out, zooming in, because this has definitely got it. but it's going to be including a lot of area that I don't even necessarily need. So I guess it's better to have more data than not enough, because is there anything more frustrating? Oh man, if I did this, I just barely might have it. Just barely. Well, I'm a gambler. I'm going to go for it. I'm going to see if I've got the whole watershed at this zoom level. So I've got the crossing here, and then hopefully all of the area to the east that is needed to delineate. All right, so I'm going to click OK. And of course, we'll know the telltale signs if I haven't got the whole area, because once I do topaz and drop my watershed outlet and delineate, then I'm going to have those flat lines that are a dead giveaway that you don't have the whole watershed. So let me turn on web services, and then it's the worldwide elevation data. Okay, that's enabled, and of course from where I defined the project location, that's how it knew where to save it. So let me click download to web, and it suggests that based on how far zoomed out we are, that we should use this 30-meter resolution. And you know, I could get higher resolution data if I don't mind waiting for it to download, and if I'm not worried about my program crashing, because you know, you can load up your RAM quite a lot with this elevation data. I'll just go with this default resolution of 30 meters, and let's see how long it takes to download. Not too bad. Okay, so I've got this area, and I'm going to have it compute topaz. Normal program termination. That's good. And the flow accumulation cell right now is set to 1 square mile. So you can see how far it goes. I think I might have got everything I need. Let's just have those flow accumulation cells extend a little bit deeper into the network. Let me change it from a mile to 0.25 square miles. So then you can see some of these other reaches. Oh, it's just going to be barely. We'll see. All right, so topaz has been calculated. Let me turn off this heat map in the background. Now, to know exactly where to put my outlet, I need to turn some mapping data on. So let me do that, get a street map going so that I can make sure I have this is the stream, and as it goes under Route 60 is what I'm looking for. So you can see now it's streaming that street map over here in the GIS data, and this is the crossing location where it goes under Route 60 that I'm going to drop my outlet. Okay, so I can bring back up the hydrologic modeling wizard, and we are at the step where I'm going to choose an outlet location. So create outlet point, and by now you know this is the part where you need to make very careful movements. It takes a steady hand. Okay, click right on that flow accumulation cell a single time. Click next. All right, now delineate watershed. Now, if I'm lucky, then I'm not going to have any of those flat lines that indicate that I didn't zoom out far enough. That's pretty lucky, right? That is pretty lucky. So I've got it all. Okay. I'm a little closer than I'd like to be down here at this bottom border, but I'm going to call it good. So we've got our watershed, and you can see that this is 16 square miles. Now I'm just going to convert that over to acres on my calculator here, because you know, I've worked at this watershed in the past, and my memory is it's around 50,000 acres. And I don't remember what's the conversion from square miles to acres. But let's just see here, area. Okay, so I've got 16.16 miles squared converting to acres. 10,352 acres. I guess my memory of this, oh, I've got these flat lines over on the side. I've just noticed that. I don't think that's going to boost it up to 50,000, but I am, you know, if I could tolerate this, I can't tolerate that. I've got some area that ought to be in that watershed that isn't. So what I have to do is throw this all out. And that's what you should do in a similar position. So what I'm going to do is I'm going to pan a little bit further down, and I'm going to pan a little bit further to the west when I start over. Okay, so I don't need to save. I'm just starting over in the hydrologic modeling wizard. Save this in the same spot, overwriting the previous file. And then here in the project boundary, okay, so I need to move a little bit this way and then a little bit that way. And I think I'll probably be all right now. Let's see. Yeah, I think it's here. You can see this little bit over here. I'm wondering if maybe that also contributes. All right, so I'll click OK. I've defined my bounds. Let's go get that data another time. Download the data at the 30-meter resolution level. It starts chugging away, and it got it quick this time. I'll turn off the heat map. I guess I ought to have it run Topaz again. So compute Topaz, normal termination. Okay, it's done that. Okay, let me turn on the street mapping data so that I can get the crossing location right. I think it's going to be right up here. So you can see it's processing, and then when it has that, it's this location. Okay. So choose outlet location, create outlet point, and click in there. Delineate watershed. Yes. So now I've really got it. I've got a little bit of extra data around the edges there. We've got slightly higher area. We mostly had it before, but now we've really got it because we can see the contour lines surround on all sides our watershed. Okay, so what do we want to do? We want to do national streamflow statistics. So you can go over here into the hydrologic modeling module, and from the drop-down box we're going to choose NSS, National Streamflow Statistics, as the model that we're working on, and then use this Select Basin tool. And you can see right now the basin's kind of on top of, let me just try and click and drag it out of the way. Select Basin. Oh, I'm clumsy somehow. Let me just double click. Maybe that'll bring it up. There we go. All right. So National Streamflow Statistics. I guess maybe another way for me to bring up that window. Well, double click. All right. So from the state, instead of Alabama, we want it to be West Virginia. And from the handout, I learned that we are in the Western Plateau region. So the Western Plateau, there's several different options in West Virginia. You can see there's a 2008 low flow Eastern Panhandle. We want the peak flow Western Plateau. So I'm going to go down here, peak flow Western Plateau. And this is the 2010 statistical regression that the USGS did, analyzing these watersheds in West Virginia. So I select that, put it over here, and it's got our drainage area. So if I click Compute Results, what it's going to do is it's going to come up with the probabilistically estimated, meaning like the 2-year return period, the 5-year return period, the 10-year return period, and so on. It's going to have the peak flow rate for each of those. So for example, if I want to know what's the likely peak flow rate that I'd see for a 10-year storm, 2061 CFS. Okay, so 2061 CFS is what I'd see out of this big 16 square mile watershed in a 10-year storm. For a 25-year storm, 2,676 CFS, and so on. All right. So we've computed the results. Another thing that's up at the top here is the max flood region. Let me show you a map that shows the maximum flood regions in the United States. So the maximum flood region for the entire state of West Virginia is in this region 4. All right, so here in the WMS program, if we say region 4, then we can, let's see, compute results. And now it's calculated this maximum flood envelope, which previously wasn't, it didn't have anything there. And so it's saying that the maximum flood you're likely to see is 31,500 CFS. So you can think of that as kind of the worst case scenario if you've got 3 converging storms at a time and a really low pressure system and a really high vertical column of cloud cover, and just, you know, the skies open up and you've got that. It's not even once in 500 years. This is like the once in 10,000 years kind of a storm that they would size a dam based on. You know, this is, you're never going to see more than 31,500 CFS coming out of this region. So it's really the upper limit of the likely flow. Now let's play around with exporting these results, because we have the results as a table, as you can see, but let's export it. And you can see it's going to export it as a .csv file. That's a comma delimited spreadsheet file that you can open up with Excel. So I'm putting into that same folder location that I'd worked with before. So I'm going to click Save, and then I'm going to open up that same file in Excel. So let me start Excel here. All right, so I'll open. All files, and there is the NFF export CSV. So click OK. So here is our peak flow rate, recurrence interval, and then some measures having to do with like the statistical quality of the data. All right. So one of the things that we could do is we could graph this. You know, we could create a graph of recurrence interval versus peak flow. So let's try that, creating a graph. By the way, since we're as a CSV right now, we probably ought to save it as an actual Excel file before we put any graphs in there. So this is going to be NFF in Hurricane. All right, now that I've got that .xlsx file, it will be able to save figures. So if I was going to create a chart of flow rate versus return period, let me do an XY scatter plot, and I will have the recurrence on the horizontal and the peak flow rate on the vertical. So let me select some data to do that. So the x-axis is going to be recurrence. I'll do starting at the 2-year, 2 through 500. And then here is the flow rate. Okay. So you can kind of see the curve there. I mean, I guess maybe I could change that to be of the sort that connects the dots. Change chart type. Let's do this one. All right. So I'll add some titles to this. This is the return period, and this is the runoff flow rate in CFS, cubic feet per second. Okay. Since we have such a long distance between some of these points, we could try making the x-axis logarithmic. So I could say logarithmic scale, and that linearizes it. And so now we've got the return period in logarithmic on the x-axis, and then on the y-axis is the flow rate. So like in comparison to the maximum, like where this was saying 31,500, that just kind of gives you an idea if this is the trend line, how many years the return period would be before you get up to 31,500. I mean, frankly, that seems awfully high to me. But I guess it's better to be safe than sorry when you're doing things like designing dams and you really want to know the absolute largest flow rate that you're likely to have. Okay, so that's basically it. Just to summarize, what are some of the steps that we went through? We did the tricky process of making sure that you've got the entire watershed boundaries. And even when you've done this a lot, like I have, you could see that it took me 2 turns to get it right and make sure that I had the entire watershed area included in that. We went through the process of national streamflow statistics, and so here in the hydrologic modeling module is where you would switch and choose between the different models that are available. We did NSS and then double-clicked to bring up that dialog box, and then that's when we let it know that we're in West Virginia and which of the models we wanted to use, in our case peak flow Western Plateau. All right, so that's it. If you have any questions, please let me know. I think it's really important for you to practice this so that you know where the buttons are, you know how to use the program, you know how to overcome some of these problems. The more practice you have, the more fluid you'll be during the exam. So that's it for today, and I'll see you on Monday.